So in the last lecture, we have seen how to use the Milne-Thompson method to find the harmonic conjugate of the given function. So we'll see some more examples based on that. Let's have the examples. Yeah, we'll see some more examples based on harmonic conjugate. So let's consider another example. Find show that the function u is equal to half of log of x square plus y square is a harmonic function, and hence find corresponding analytic function f of z and its harmonic. Okay. So here we have a given function. We want to find out that this function is a harmonic function, and then after we know that this function is a harmonic function, we have to find out the corresponding analytic function. And once we know the analytic function, we have to find out what is its harmonic conjugate. So let's try the solution. What we have is like f of z is equal to u plus iv e and analytic function with, okay, so now u is given, so we can have this real part u is equal to half of log of x square plus y square. Okay, now we want to show that this is the harmonic function. So we have to find out the second order derivatives and show the sum is going to be 0. Okay, so for that we consider, as we also have to find out the analytic function. So we have phi1 of xy is equal to w by wx, and that's what we will be having half of 1 upon x square plus y square, and the derivative is going to be 2x. So this 2 will get cancelled, and you will be having x upon x square plus y square. So we get here phi1 of xy is equal to, this is going to be x upon x square plus y square, let it equation 1. Now we want to find out that this function is going to be harmonic, so we want the second order derivative, and hence differentiate this once again with respect to x. So we get hence we have double square u by double x square is equal to, so we have to use u upon v rule here. So x square plus y square into the derivative of this term is going to be 1 minus this term remains as it is, and the derivative of this term, so it is going to be 2x upon v square. So you have x square plus y square bracket square. So if we simplify this, we get x square plus y square minus 2x square upon x square plus y square bracket square. Okay. And now we get gamma square u by gamma x square is equal to y square minus x square upon x square plus y square bracket square. That is equation 2. Okay, so we got the derivative with respect to x, the first order derivative, and the second order derivative. Now we have to consider the derivative of this given function u with respect to y. So let us see the derivative of this function with respect to y. Now we have I2 of xy is equal to w by y. So here we have this half as it is, and then you will be having 1 upon x square plus y square into the derivative of this term with respect to y is 2y. So this 2 will get cancelled, and you will be having y upon x square plus y square. So we get here y2 of xy is equal to y upon x square plus y square. That's what we have. This is equation 3. Okay. So we got here the first order derivative of u. And now to prove this function as a harmonic, we need the derivative with respect to y, the second order derivative with respect to y. And hence we have gamma square u by gamma y square. So the derivative of this term with respect to y, what is the term you'll be having here? This is x square plus y square, and the derivative is going to be 1. Again, we have to use u upon v rule. Now see, this y remains as it is, and the derivative of this denominator, so it is 2y. And v square, so you'll be having x square plus y square bracket square. Okay, so let us simplify this. So we got x square plus y square minus 2y square upon x square plus y square bracket square. So we can simplify this as x square minus y square upon x square plus y square bracket square. So here we have to be careful that we cannot factorize the numerator and the denominator. Okay, and there is no common factor that we can cancel. So please be careful. So we get double square u by double y square is equal to x square minus y square upon x square plus y square bracket square. That is equation 4. Okay. So here we got the second order derivative with respect to x, and here we got the second order derivative with respect to y. Now we have to check whether this u satisfy a Laplace equation or not. If it satisfies Laplace equation, then it is going to be the harmonic function. If it does not satisfy Laplace equation, then we say it is not a harmonic function. So let us see. And what we can do is we can adding equations 2 and 4. Okay, we get. So what we are able to get is see the terms. Here we have double square u by double x square plus double square u by double y square is equal to, what we get is y square minus x square upon x square plus y square bracket square plus x square minus y square upon x square plus y square bracket square. See from equation 2, this is equation 2, y square minus x square upon x square plus y square bracket square, and this is equation 4. Now we simplify this, so we can have y square minus x square plus x square minus y square upon we have x square plus y square bracket square. So you can see this y square and minus y square, this minus x square, and so we can get it 0. So actually what we got is we got double square u by double x square plus double square u by double y square is equal to 0. Okay. So we got this equation is equal to 0. But you know what this equation is? This is Laplace equation. So we can say that is Laplace equation is satisfied. Okay, and once we get the Laplace equation satisfied, so we can say the function is the function we have u. Okay, so the function u is harmonic. So this is going to be the harmonic function. Okay, so now we got the first part completed for this example. Now we want to find out the analytic function f of z. So to find the analytic function f of z by Milne-Thompson method, first we require the function and its real or imaginary part. Then we require the first order derivatives that we have already calculated. And now if we have done with the second step of Milne-Thompson method, then we have to follow the third step of Milne-Thompson method. So what we do in the third step of Milne-Thompson method, we put x is equal to z and y is equal to 0 in equations 1 and 2. Okay, and after that we get. So we have to find out what is phi 1 at z0, and we want to find out what is phi 2 at z0. Okay. So phi 1 at z0. See what is the phi 1 that we have. Okay. So we have phi 1. So this is going to be z upon z square, and this is going to be 0. Okay. So it is z upon z square. So that's going to be phi 1. So it is z upon z square. I can write 1 upon z. Okay. What about phi 2? So we have phi 2. Y is going to be 0 here, and hence this term entire term will be 0 because the numerator is going to be 0. Okay, so we can write here this numerator is 0, so this is going to be 0. So what we got is phi 1 of z0 is equal to 1 by z, and phi 2 of z0 is equal to 0. So the third step of Milne-Thompson method is completed. Now we have to go for the fourth and final step. So what we can say is by Milne-Thompson method, the analytic function f of z is given as. So what do you have f of z? Always write the formula. So integration of phi 1 z0 dz minus I integration phi 2 of z0 dz plus c. So what you have here, where c is constant of integration. C is going to be constant of integration. Now we know what is phi 1 and what is phi 2. So we are able to write here f of z is equal to integration. So this is 1 upon z dz. Then we have minus I integration 0 dz plus c. Okay. So let's have this. what is the integration of 1 upon z? So it is going to be log of z and plus c. So we got f of z is equal to log of z plus c. So this is what the analytic function we are able to get. Okay, so we can say this is the required analytic. Okay, that's what we have. Now we have completed the second part of this example that we wanted to find out the analytic function. So first we showed that this is the harmonic function. Second part we calculated the corresponding analytic function, and now the third part we have to find what is the conjugate. Okay, so harmonic conjugate of the given function. And hence for harmonic conjugate, what we will do is we put z is equal to x plus iy in above equation we have. So what we'll get is f of z is equal to log of x plus iy plus c. Then what we know is you have seen in the first semester that log of complex number. So what we know is log of x plus iy is equal to we have half of log of x square plus y square plus we have I tan inverse of y by x. Okay. So this is the formula that we have for the log term, and hence we can write this as this is half of log of x square plus y square plus I tan inverse of y by x plus c. Okay. Now once we have this f of z, so what we can do is we can compare the real and imaginary part of the analytic function. Okay, and hence we write comparing real and imaginary parts we get. So what we are able to get is u is equal to half of log of x square plus y square, and v is tan inverse of y by x. Okay, so you got u and v. Now the question is whether we got this correct or not. Okay, so we can verify ourselves by comparing the given thing. So this is what we have calculated, and now compare this with the given. Okay, so see what is given to us. Okay, if we see what is given to us, u is equal to half of log of x square plus y square, which is exactly what we have obtained. Okay, so if we are able to get back the given thing as it is, that means your another part is correct. Okay, so if you are able to get this part correct, then this part will be definitely correct. Okay, and hence we got this correctly, so this is correct, and hence we say the harmonic conjugate of u is equal to tan inverse of y by x. So this way we are able to get the harmonic conjugate of the given function. Okay. So do you have any doubt in this example? Are you able to get this example? Do you have any doubt? Okay. So Yeah. Who has written that formula wants to know? Please unmute yourself. Gaurav. Yeah. Okay.
Yes, sir.
So you want to see how we have derived that formula, correct? No? Yeah. I'll show you. No.
Yes, sir. I don't remember that one.
Yes. Yes. I'll show you. Sure. Sure. Okay. So let us see that I'll show you. No problem. Yeah. Okay. So this formula you are not able to get, correct? Okay. Surely I'll show you how this formula is derived. Okay. So let us solve it here. Okay. What we have to find out what is log of z. Okay. So let z is equal to x plus iy. Correct. Okay. So we have this z is equal to x plus iy. So we know r is equal to mod z is equal to square root of x square plus y square. And we know theta is equal to argument of this z, which is tan inverse of y by x. So we know that z is equal to, we can write z as e raised to I theta. This is the Cartesian form and this is the exponential form. Okay. And now consider log of z. So we consider log of r e raised to I theta. Okay. What we know is, we know log of a into b is equal to log a into plus log of b. Okay, so simply here we can write as log of r plus log of e raised to I theta. Okay, moreover, this is the natural base. Okay, so in mathematics, when we consider log or when I write log, that is always so log is always log to the natural base e. Okay, and what we know is so general formula for log to the base x, x raised to m is equal to m. Okay, so log of x raised to m to the base x is m only. So here we have this is log of r plus this will become I theta. Okay, what we know about r, so it is a log of square root of x square plus y square and plus this I theta. Okay, now what we know is we can write this as this is equal to, so this is log of x square plus y square bracket raised to half plus I. This is tan inverse of y by x. So I can write this as half log of x square plus y square and plus I tan inverse of y by x. And what we were solving actually log of z. Okay, so this way we are able to find this formula. So this actually we have done in same one. Okay, so is it clear to you now? Gaurav?
Yes, sir. Understood. Thank you.
Okay, that's good. Okay, so you got this now. Great. Okay, and hence we come back to our topic now. Okay, so we are done with this example. Let's have the another example. So we go with another example. Then show that. Is there any other doubt? If there is any other doubt, then I'll solve that and then we'll go for the next example. Okay, so is there any other doubt? Okay, no problem. So we'll go for the another example. So if you have any doubt, please feel free to ask. Okay, so here we'll go with this example now. So that the function e is equal to x square y plus 6xy minus y cube is harmonic, and hence find the corresponding analytic function f of z and its harmonic conjugate. Okay. So here we have given a function v, and then we have to show that it is harmonic. And after showing that it is harmonic, we have to find the corresponding analytic function and its harmonic conjugate. Okay. So let us try this example. Let us find the solution. So what we have here, like as we want to find out the analytic function. So first step is always let f of z is equal to u plus iv t and analytic function with so this is going to be v. So we know it is imaginary part. Imaginary part v is equal to 3x square y plus 6xy minus y. Okay, so that's what we have. Now find the derivatives. Okay, the first order and second order derivatives. So consider psi1 of xy. Be careful while finding the derivative. This is the imaginary part. So we'll be having dabba v by dabba y first. Okay, so with respect to y, we'll have this is 3x square plus 6x, and I'll be having minus 3y square. That is equation 1. Then dabba square b by dabba y square. So this is going to be 0, and I'll be having this minus 6y. That is equation. Now we got the derivative with respect to y. Okay, so we have to consider the derivative with respect to x. So now we have psi2 of xy, that is dabba b by dabba x, is equal to the derivative with respect to x. We have 6xy plus 6y. That is equation 3, and we get dabba square b by dabba x square. So the derivative with respect to x again. So I'll be having this is 6y. The derivative of this term is going to be 0, and this equation 4. Okay. Now what we get here. So we want to show that this is the harmonic function. So we have to add these two equations, equation 2 and 4, and see that whether they give us the required result or not. So what we can do is adding equations 2 and 4 we have. So what we'll get here, dabba square v by dabba x square plus dabba square v by dabba y square. So this is 6y minus 6y. That's going to be 0. Okay. So we can see we got a result that dabba square v by dabba x square plus dabba square v by dabba y square is equal to 0. So please be careful while writing. Okay, the notation should be clear and perfect. Okay, so what is the key? This is the Laplace equation. So we can say that is Laplace equation is satisfied. So we got Laplace equation satisfied. That means this function is harmonic. So we can say function E is harmonic. Yeah, this function V is going to be harmonic function. Okay, so we got the first part of this example completed. Now we have to find the analytic function. So to find the analytic function, we have already completed two steps of Milne-Thompson method. The first step is declaring the function and its real or imaginary part. Second step is finding the first order derivatives, that is psi1 and psi2. And so we have to go for the third step. Okay. So what is the third step we have? Hence, put x is equal to z and y is equal to 0 in equations 1 and 2. So we have, what will be having, see this equation 1. Okay, so we have to put here x is equal to z and y is equal to 0. So this will be 3z square. This is 6z and this term will be 0. So 3z square plus 6z. Okay, so psi1 we have psi1 at z0 is equal to 3z square plus 6z, and we have psi2 at z0. Okay, so psi2 at z0 we have to consider. So what is psi2? See this psi2. So here I am putting x is equal to z and y is equal to 0, and both the terms contain y, so this term is going to be 0. So we get psi2 is equal to 0. So this psi2 is 0. Okay, so we got psi1 z0, we got psi2 z0, and hence we are able to write the final and fourth step of Milne-Thompson method. So we can say by Milne-Thompson method, the analytic function of z is given as. So I always insist you to write the formula so that you will not go wrong. Okay, and hence what is the function we get here? So f of z is equal to integration psi1 of z0 dz plus I integration psi2 of z0 dz plus c. Okay, so where c is constant of integration. Okay, so this is going to be the constant of integration. Now we know psi1 and psi2, so we put the values of psi1 and psi2 here, and we are able to get as f of z equal to integration. So this is 3z square plus 6z dz plus I integration 0 dz plus c. So we have here this is equal to, so it is 3z cube by 3 plus 6z square by 2 plus this term is 0, so we can now see. Okay, so we can write this as z cube plus 3z square plus c. And so we got f of z is equal to z cube plus 3z square plus c. So we can say this is the required analytic function. Okay, so that's what we have, the analytic function. So we are done with the second part of this example. So you can see first we have to show that this is the harmonic function. We showed it. Then second part is find the corresponding analytic function. We calculated. Now the last part we have to find its harmonic conjugate. Okay, so let us try to find the harmonic conjugate. So what we have to do to find the harmonic conjugate? we have to replace this x by this z by x plus iy and separate the real and imaginary part. So what we can do is we can have put z is equal to x plus iy in above equation we get. Okay, so what we are able to get is see f of z is equal to x plus iy bracket cube plus 3 x plus iy bracket square and plus c. Now we know x plus iy bracket cube. So a plus b bracket cube, a plus b bracket square, and hence we are able to simplify this like this. See the first bracket, I'll be having x cube plus 3i x square y minus 3x y square minus I y cube plus 3. We'll be having x square plus 2I xy and minus y cube plus c. So here what we have, I square is equal to minus 1 and we have considered I cube is equal to minus I. Okay. So this is I cube here. So I have written as minus I. This is I square here. So it is going to be minus 1. This is I square here. So it is minus 1. And now find the terms with I and without I. So I'll be having x cube minus 3xy square plus 3x square minus 3y square plus I 3x square y minus y cube and plus 6xy plus c. Okay, so that's what we are able to get. Now compare with the real and imaginary part. Okay, so we can say pairing uh, real and imaginary parts. We have. So what we'll be having? U is equal to x cube minus 3xy square plus 3x square minus 3y square and b is equal to x square y minus y cube plus 6xy. Okay, so here we have a checkpoint that whether we have calculated correctly or not. So see what is given to us. V was given. So V is what you'll be having 3x square minus y cube plus 6xy. Okay, so that's what we have. Okay, so it is x square y minus y cube. Now check this is what we have got correctly or not. And if we have got V correctly, that means this part is correct. So let's check what is V given to us. Okay, so you can see V is 3x square plus 6y xy minus y cube. It is exactly same what we have got. Only we have to rearrange the terms. Okay, so terms are same. Only order and in addition the order doesn't matter. So this is exactly what we have obtained, which was given to us. That means if this is correct, this is also correct. Okay, and hence what you can say is we want the conjugate. Okay, so harmonic conjugate of V. So we can say uh, harmonic conjugate of V is 2 is equal to x cube minus exy square plus 3x square minus 3y square. Okay, so this is what exactly we are able to get, or we are able to get the harmonic conjugate. So, do you have any doubt in this example? That's great. Good, Akhilesh. Okay. Okay, so we are done with the harmonic conjugate now. Okay, so now we have to explore the another concept. Okay, so another concept related to the analytic function. So let us see that concept which is related to the analytic function. So we have the another concept related to harmonic function is orthogonal. So orthogonal trajectories. Okay, so this is the concept that is related to analytic function. Now the question is how this concept of orthogonal trajectories is related to the analytic function. So we consider that f of z is equal to u plus iv p and analytic function. So suppose this is analytic function with real part u of xy and imaginary part e of yeah. So this is the usual notation. U and v are the real and imaginary part of this analytic function. But there is one more relation between this u and v. They are not only the real and imaginary part, but if we have a family of curves using this u and family of curves using this v, then these two families are orthogonal trajectories of each other. Okay. We can say then u is equal to c1. Okay. Then the family of curves u is equal to c1 is the family of curves. This is the family of curves. So I'm writing a family of curves is orthogonal trajectories of the family of curves E is equal to C. And we can say the otherwise also. So the family of curves B is equal to C2 is orthogonal trajectories of family of curves U is equal to C1. Okay, so up to it we were knowing that this U and V are the harmonic conjugate of each other. Yeah, so first we have seen that the u if f of z is equal to u plus v is a analytic function, then u and v satisfy CR equation. Then after that we have seen if f of z is equal to u plus iv is analytic function, then u and v are harmonic conjugate of each other. And now we are claiming that if f of z is equal to u plus iv is an analytic function, then we have two families of the curves. U is equal to C1. This is one family of curve. and V is equal to C2 is another family of curve, and we are claiming that they are the orthogonal trajectories of each other. Okay, so orthogonal trajectories, if they, I claim that they are orthogonal trajectories of each other, then the question is how they will look like, or what is the nature of their, or why we characterize them as the orthogonal trajectories of each other. Okay, so we'll have okay, see, the curves we are having here. Okay. So I'm having one family of curves, okay, and the other family of curves. Okay. So this is x-axis, this is 0, this is y. I'm considering the one family of curves. So we can have x square plus y square is equal to c1. Okay. So if I change c1, okay. So suppose c1 is equal to 1. C1 is equal to 2, C1 is equal to 3, then C1 is equal to 4. Okay. So, can you name this family of curves? What this family is? From the equation, you are able to get it. What is family of curves is? Can you name this family of curves? X square plus y square is equal to the constant. Yes, it's a circle family. Okay, so when we say circle, then it is going to be only one. Okay, when we say the concentric circles, okay, so this is the family concentric circles. Concentric circles means their center is always the origin. Okay, and the radius is different. So this constant gives you, if I put only one value, then it will be only one circle. But if I put the different values of this constant, then I am having this is a family of curves, and so I can have there maybe there if I change the value of c, so c is the constant, it will have the infinitely many values, and hence we can have infinitely many curves. Okay, so the question is, do this family has any real coincidence or real life applications? Okay, so yes, actually, okay, if you see, suppose you consider uh, electric conducting wire, or electric, suppose a wire, and then electricity is passing through that wire, then the flux, electromagnetic flux around the wire is actually in the concentric circles. Okay, so that's what we have. These are the concentric circles you can have. Yeah, so this way there are many applications. This is one of them. Yeah, and now we have to find the another family. So see here, I'm drawing the another family. You identify this family. Okay, what this family of curves is. Yeah. So please identify this family of curves. Okay, so this is another family of curves I have drawn. Okay, can you guess what this curve is? Yeah, yes, good. So both of you got it. So this family of curve is a family of straight lines passing through origin or y is equal to mx. Perfectly all right. Okay, so good. Okay, and now you can see this family is actually y is equal to c2x. Okay, so instead of mx, I am writing c2x. So this is the one family that we have. X square plus y square is equal to c1, and this is the another family that we have. Y is equal to c2x. Now you can see, okay, that each member of this family is intersecting each member of this family in 90 degree. Okay, so these lines are intersecting all the circles in 90 degree. Or another way, these all circles are intersecting all these lines in 90 degree. So I claim that this is one family, this is the another family, and these two families are intersecting each other. Each member of this family U and each member of this family V, they are intersecting each other in 90 degree, and hence they are called orthogonal trajectories of each other. So this is the concept of orthogonal trajectories. So there are so many applications of these orthogonal trajectories in electromagnetism, in thermodynamics, in magnetism only, in wave theory, electromagnetic wave theory, and so many. Okay, so there are so many applications of these orthogonal trajectories, and that's why we basically started from the analytic function. Let us try to understand the analytic function. So we got the analytic function, then slowly we consider the concepts related to analytic function, and now we are ready to understand the applications. So there are so many applications, and that's why we have to study. Okay, so is there any other doubt in the definition of an orthogonal trajectories? You got the idea of orthogonal trajectories? That's good. Okay, very good.